Alright everyone, this video's gonna cover just general ideas about enthalpy, which is delta H, and then I'm gonna talk about one way to solve enthalpy problems, which is using stoichiometry, or a variation of stoichiometry. Alright, the way we're going to look at enthalpy in this class is we're going to look at it all about heat. So if heat is absorbed, we say that's endothermic, or if it's released, it's exothermic. All of this needs to be under constant pressure. So if it is constant pressure, the pressure is not changing in the reaction at all, our delta H, our enthalpy, is going to be equal to heat, which is Q. And we learned about Q during our Q equals MCAT and our phase changes. Kind of like first semester when we learned about, 15 different K values, KC, KQ, KSP, KA, KB, the list went on and on and on. Delta H, or enthalpy, has variations of delta H, but really they're all kind of looking at the same thing. They're looking at heat, but we use these kind of little subscripts to explain maybe more specifically what we're looking at. So heat of reaction is how much heat is absorbed or released by a reaction. Heat of combustion is how much heat is absorbed or released by a combustion reaction. Heat of formation is how much heat is absorbed or released when we are forming or making 1 mole of a substance from its bare bones basics. And then heat of fusion and heat of vaporization, we saw those when we did the phase change calculations for melting and freezing, and then boiling and condensation. So enthalpy is what's called an extensive property, which basically means it does depend on how much of the substance or how much of a reactant or a product you're producing. Usually you'll see the units in kilojoules per mole, letting you know that it does depend on the amount. That per mole tells you it depends on the amount. If I decide to reverse a reaction, so instead of making the product, I say I'm going to use up that product and kind of push the reaction the other way, delta H is equal in magnitude, but you change the sign. So if I have negative 50 kilojoules per mole as my forward reaction, if I end up reversing the reaction, it's going to be 50 kilojoules per mole. Same value, just opposite sign. And the enthalpy change does depend on the states of matter. So you'll see in this unit, we will always put the states in the reaction, solid, liquid, gas, after each reaction or product, because solid water, liquid water, gaseous water have different enthalpy values that are associated with making or using them. All right, the two main vocab words that go with delta H are exothermic and endothermic. So let's talk about exothermic first. Exothermic is when heat is released by the system. This means the surroundings will feel hot because my reaction is giving off heat. So usually we can see an increase in temperature if we're measuring temperature. When we record delta H, or the enthalpy, it will be negative. And you see, we've seen these graphs before, but we have an enthalpy value for our reactants. We know about this transition state from kinetics, so we get all the way up. We get to the point of no return, we fall back down, and you notice the energy of the products is less. So the difference, let me switch up my colors. This difference from start to finish right here is my delta H value, and it's going to be negative if the reaction is exothermic. Some just general examples of things that are exothermic: phase changes when we're cooling down, so gas to liquid, condensing, or liquid to solid. If we combust anything, that's going to give off energy, so your car burning its gasoline, any sort of fuel, hydrocarbons being burned, things like that. Anytime they're like, oh, the reaction got hotter, the temperature increased, that's exothermic. Or if I'm looking specifically at a reaction in terms of the bonds, anytime you make new bonds, that's exothermic, or release in energy. Endothermic is the opposite. It's where heat is absorbed by the system, so the surroundings are usually going to feel cold. You might see a decrease in temperature. If you look at the graph, we start with our reactants, we go up, we get to this transition state, or the coordination, or the transition complex, and at the point of no return, we fall back down, but you notice that the products have a higher energy than the reactants. So when we get our difference, this value here, that's our delta H, our enthalpy, and it's going to be a positive value. So positive for endothermic means we're absorbing heat, negative for exothermic, we are giving off heat. Some generic examples of endothermic reactions or processes: anytime you're heating up for a phase change, so a liquid turning to a gas, solid to a liquid. Anytime they say, oh, the temperature of the system went down, or the whatever you're looking at, it got colder. And then anytime if we're looking down to the level of the individual bonds, anytime I'm breaking bonds, so turning a diatomic molecule like F2 into just regular F, right? We're breaking the bonds between those two F atoms to just two separate F fluorine atoms. That's going to be an endothermic process. All right, there are usually like 5 types of enthalpy problems. You already watched a video and did a lab where you had to use calorimetry and use Q equals MCAT to solve the problems. Some things you look for in those is if they give you a before and an after temperature, if they give you specific heats, things like that. Usually they'll say there's a calorimeter. Huge clue, super helpful. The next type of problem we're going to talk about today is using stoichiometry to solve. So for stoichiometry, you're going to look for a couple different things to know that you should use stoich. Usually they're going to give you the balanced reaction, which is very nice, and they're going to give you the delta H of reaction. So they will specifically say the delta H for this reaction, and then usually they're going to give you some sort of amount of reactant or product, kind of looking like a stoich problem. I'm going to be honest, I think these are the hardest to identify. So usually once we learn all of them, we'll use process of elimination, and if it's not the other 5, then it's going to be stoichiometry. All right, here's our first problem. So we have a balanced equation, and they give me, this is the delta H of the full reaction. So anytime this reaction goes once, when 1 mole of methane and 2 moles of oxygen react, we are going to give off this much energy. How do I know we're giving it off? Because it's a negative. So this is an exothermic. Just pretend that says exothermic. Exothermic reaction because delta H is negative, so we are giving off heat. Heat is a product in this reaction. So they want to know how much heat is given off when we burn 4.5 grams of methane, and methane is CH4. So they're giving us our superstar. I'm going to assume it's excess oxygen. Most of the time they won't make you do a full stoich with figuring out limiting and stuff like that, so that's kind of nice for these. So my first step, I have to turn the 4.5 grams of methane to moles of methane, so I just quickly calculated the molar mass. Took my 4.5 grams of methane, I'm going to multiply it by this fraction here. 1 mole of CH4 is equal to 16.05 grams. That's what molar mass means, so my grams cancels, and I'm left with moles of methane. At this point, you could do a full-on stoichiometry BCA table. It would be an easier one because we already know methane is the limiting, but usually with these problems, I'm going to be honest, I just look at the relationship between the coefficients because it's usually not even necessary to do a full before change after table. It's just kind of is extra work, but you can. If that's comfortable for you, great, you can do a BCA, but I usually don't. So what I'm going to look at here is I know that there's negative 890 kilojoules, or 890 kilojoules given off for 1 mole of reaction, one time this reaction happens. And if I look at this reaction, for one time the reaction goes through, there is 1 mole of methane used. So that's going to be the important relationship. So I found how many moles of methane there are in 4.5 grams. I'm going to use that down here, and I'm going to use the idea that for 1 mole of CH4, I'm going to give off negative 890 kilojoules, or 890 kilojoules are released. So I solved that guy, that way moles of CH4 cancel, I'm just left with kilojoules. So my answer is negative 250 kilojoules, or you could say 250 kilojoules of heat is released. Remember, released and negative are synonyms, so you can either finish right here as your answer, or I'm looking for that word released to let me know that you understand that it's exothermic. All right, looking at this reaction, we have to decide if it's endo or exothermic. So I go straight to my delta H of reaction, and I see that it's negative, so I know if it's negative, that is exothermic. Heat is given off, heat is a product, heat is released, however you want to think about it. So it is an exothermic reaction. Question B says, what is the delta H when 2.4 grams of magnesium are burned? So I know if 2 moles of magnesium are burned, it's going to give off 1,204 kilojoules, but I'm guessing that 2.4 grams is not equal to 2 moles of magnesium, so we have to do a little stoich. So for this problem, I'm going to turn 2.4 grams of magnesium to moles of magnesium just using the molar mass, so magnesium 24.31 grams per mole. My grams cancels, I'm just left with moles of magnesium. So what I know from this, I have moles of magnesium, but I know that negative 1,204 kilojoules is released when there's 1 mole of reaction happening. But for 1 mole or 1 time this reaction goes through, I need 2 moles of magnesium because of the stoichiometry. So I'm going to take my moles of magnesium that I found, and I'm going to say, well, for every 2 moles of magnesium, I'm giving off negative 1,204 kilojoules. So I can solve that out. Moles of magnesium cancels. I get negative 59 kilojoules. Same idea. You can either leave this as your answer, or you can say that magic word release to let me know that you understand it's exothermic. All right, looking at question C, how many grams of MgO are produced when the enthalpy change is negative 96 kilojoules? So I can already guess that it's going to be less than 2 moles, because if I make 2 moles of MgO, I'm releasing I'm giving off 1,204 kilojoules. This is much less than that. So I anticipate we're going to make less than 2 moles of MgO. This one's kind of working backwards. So I'm going to start with this relationship. If I have 1 reaction going, I'm going to give off 1,204 kilojoules, and for 1 mole of reaction, I make 2 moles of MgO. So let's start with what's given, which is the negative 96 kilojoules, and we're going to use this idea, this relationship here. If I give off, my enthalpy is negative 1,204 kilojoules, for every 2 moles of MgO made, my kilojoules cancels, and that tells me I should be making 0.159 moles of MgO, which goes with my prediction. It's much less than 2 moles because negative 96 kilojoules is much less than 1,204 kilojoules. Once we have the moles of the magnesium oxide, I'm just using the molar mass to cancel out moles. 1 mole is equal to 40.31 grams, so that way I get how many grams of magnesium oxide will be produced. All right, and lastly, letter D is kind of a weird twist. So let's see. It says, what is the change in enthalpy when 7.5 grams of MgO decompose? That word's going to be important in a minute. So first, I'm going to do what we've been doing, turn 7.5 grams to moles. We know the molar mass of MgO from the last slide. So 1 mole is 40.31 grams. We get into moles of MgO. So I'm going to use that guy in a second. Let's read this. So we know that we give off 1,204 kilojoules for 1 mole of reaction, and we produce in 1 reaction 2 moles of MgO. But that's producing MgO. Decomposing means we are looking at the reverse reaction. Okay, so we know from an earlier slide that the reverse reaction has the same magnitude, 1,204, but opposite signs. So instead of releasing energy, we are going to absorb any energy in this one. We need a positive 1,204 as our value for enthalpy. So let's check out, here, I flipped the reaction here. Let me zoom. So all I did was write the reverse reaction and made that delta H positive, so you could see that's the only change when you flip the reaction. All right, so we take that moles of magnesium oxide, we start with it here. The only difference now, for every 2 moles of MgO that's decomposed, it's positive 1,204 kilojoules. So we get 112 kilojoules, or you can have that word absorbed, so it's a positive value. All right, to wrap up these notes, I would like you to calculate how much heat is released or absorbed when 45.8 grams of hydrogen reacts with excess NO2, so that's our superstar, by using the heat of reaction and the balance equation. Pause your video, and I will put the answer on the next slide so you can check. Hopefully you got right around negative 697 kilojoules, or the phrase 697 kilojoules is released because it's an exothermic reaction. Thanks for watching.